how can you communicate using an electronic electronic signal, essentially. So I'm not going to actually do anything with, a microcontroller or something. I'm just going to explain how one can manipulate a signal to to send information, to communicate, basically. Okay? So, well, there's two modes to do it, okay? Let me get a new pen. This one's pretty broken. So you have digital, and then you have analog. Okay? I probably spelled that wrong. There we go. So you have these two separate modes for communicating, for sending information through an electronic signal. So first off, let me clarify, what do I mean when I say electronic signal? All I mean is something sent through, a wire, just a wire using electrons. That's what I mean. Or I even mean something sent through an antenna, which again can just be, just a piece of wire, just like that, sent over electromagnetic waves. So it can sent be via, photons or electrons. But we're going to focus today on electrons. So just how can something be sent through a wire? Okay, so you have your two camps, analog and digital, right? Digital is easy to explain, okay? Digital, well, there's really sort of three, but digital you can explain is that you have signal levels, okay? So, the signal can be between such and such, we'll just say ground and 5 volts, and the signal will alternate between the two separate signal levels, right? And usually people say this is a 1 and this is a 0, right? So that's what digital means. They're set signal levels. The signal really can't be between these levels except when it's transitioning. So, the signal really can only be at these two levels. Analog, the signal's also got to be between a set voltage, so we'll call this ground, and 5 volts again. Analog, the signal can be at any level, so you can have a sine wave or a sawtooth or anything really. That's all a legitimate analog signal. So analog, the signal can be at any level, and digital, the signal really is stuck to the specific levels. Okay? So let's talk about some examples of these two, right? So digital, you've probably heard of SPI, I squared C, U heart, etc., right? Analog, you have the old TV signals, so you have TV signals just like these TV plus and minus on the oscilloscope triggering. That's what they're meant for. You have the TV signals, VGA, another type of TV signal. Audio, that's another way. So those are some examples of how each of these works, okay? So you can, and now how can you, distinguish between them? Well, it's pretty simple. Digital, you're going to see something like this if you look at it on a scope. And analog, you're going to see something like this. It's going to vary, okay? They're quite easy to distinguish between. But now, right, how is the information actually transferred, okay? So let's start with digital. So with digital, you have, say, two values. We'll start with two values to begin with. So you have 5 volts and ground. All right, just to make it simple. And each of these is assigned a value, and this significance can be assigned anything. So like I said before, ground is usually assigned 0, 5 volts is usually assigned 1. So this is, say, 0, 1, 0, right? It doesn't have to be assigned that way, right? That's the way people are usually called it. But you could assign, because that way you can read it out in binary. You don't have to do that, though. These values are just arbitrarily assigned. So you could assign this a value of smiley face, and this a value of frowny face, right? You can really assign it a value of anything. You can make this 5 and this 7, and then your code will only be able to work in 5s and 7s. That's it really doesn't matter. So how can you take these values of smiley face and frowny face, or zeros and ones as they're commonly used? Well, if you string them together in a chain, right, like that, you can get a binary number. So a binary number is a way to represent a number between to way to represent a decimal number using only ones and zeros. So each of these will correspond to a specific power of 2. So in this case, this could be 2 to the 0, and this would be 2 to the 1, and this would be 2 to the 2, and all the way up until 2 to the 8th we have here. Okay, and then the sum of all of this would be the maximum number. And in this case, the maximum number you can display with all of this is this is an 8-bit number, 1, 2, 3, 4, 5, 6, 7, 8, and so it's 255 bits you can display with an 8-bit number. A 10-bit number, you can go, at least this one, you can this most significant bit, as it's called. So you have the two ways of naming them: most significant and least significant. Okay, and that just corresponds. The most significant bit is this one, most significant, and the least significant is this one. And you'll have what's called most significant bit first, or least significant bit first. Least significant bit first means 2 to the 0 is coming first. Most significant bit first, it means 2 to the whatever. You have 8 bits, you have 16 bits, you have 100 million bits. Doesn't matter. That's so it's pretty simple. Okay, that's how you know. And it's often a pain to figure out which one a system is using if you don't know, because they can alternate. So the way binary works really is it takes a string of numbers and it converts it into a decimal number. Okay, so in this case, 2 to the 0, but there's no 2 to the 0. There is 2, so this would be 2 plus, then we have 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, or this actually be 2 to the 7, sorry. 2 to the 5 and 2 to the 6, because it starts at 2 to the 0. So we'd have plus 2 to the 5, and then plus 2 to the 7th, right? And that would give you your decimal number. Okay, and that's how digital values work. They assign things, values of ones and zeros, which can be converted to binary, and which can be then converted into a decimal number, which your code can use. And then, or you can take this string of numbers, you can convert it to a decimal number, which can then be converted into characters. Right? So, for example, 1001101 is a capital M in ASCII. What's commonly standard for converting binary into decimal and character values. Okay? And by character, you can also convert it to symbols, carriage returns, whatever. So this could be $, whatever. So that's the common way that digital is done. That's how you can actually send information via electronic signal. Analog is somewhat different, right? So this is commonly used with microcontrollers and digital systems, obviously, because digital will use a digital form of communication. Analog's used with analog systems, obviously. But the way they're processed is very different. So it's much more difficult to process analog most of the time, because stuff like Arduino, this is a totally digital processor. But analogs more oftentimes are not processed by a discrete circuitry, at least in the designs that hobbyists can make. I mean, you can buy analog processors and analog FPGAs and stuff, but they're quite complicated to use. But the way analog usually works is you can have the signal. So if it's an audio signal, it'll just be like, something like that. And then you can plug this straight into some speakers, and you can hear the information that's being transmitted via the signal, which is the audio. This is actually going to be the frequencies of the sound waves. So this is just direct. But you also have what's called amplitude modulation. This is another way to send signals. And amplitude modulation is going to take a carrier wave of a higher frequency, and it's actually going to modulate it into the actual signal. So this, what happens is when you low pass filter it, you actually get something that looks like this, right? With this corresponding to this, this corresponding to this, and this corresponding to this, okay? And in that way, you can use a much higher frequency, which you can then send over via antennas or something, and convert it down into a lower frequency. And this is commonly used to send audio and stuff. So this is how you can send information via the analog domain. And then this can get played over a speaker. You can also do frequency modulation, which is done via a phase lock loop. They're quite complicated, but there's better places to find them on the internet. So I won't do a video on phase lock loops right now. But you send it through a phase lock loop and you get the frequency modulation. But you can also don't change the analog, but what frequency modulation is you just change the frequency. So it's, it's tight and then it's loose and then it's tight and, whatever. That's frequency modulation. You send this back through a phase lock loop again and you're going to get the original signal out. So those are ways that you can actually send information via analog and digital signals, okay? And this is the way a lot of things work. You can also sort of have hybrids, if you will. So these hybrids are interesting. These are more so digital signals, but they have an interesting hybrid. So they have, like digital, they have a level, like ground, and then they have this top level, like 5 volts, right? Then they can have more levels. Right? And the signal can actually exist at any of these levels, but not in between. So it's sort of like a hybrid of both of the types. So the way these signals work is they can actually exist at any of the levels. So, they can look something like this, right? And now, instead of the values being assigned something like 1s or 0s, you can assign ground as 1, 1, 1 volts as 1, 0, and then as 0, 1, and then as 0, 0, right? So that'd be if you only had 3 levels, right? Just like that. You could actually get double the density, double the bit density for the same signal. The problem here is that you have to process the multiple levels, okay? And then past that, you can start going 0, 0, 0, and then 0, 0, 1, right? And then you would have to keep going and going. But using this multiple signal system, you can actually split it up to increase your bit density and increase thus your bandwidth, because you're actually sending more data in the same signal because you have multiple levels, and so each level can mean twice as much. So if you only have a 4-level system instead of a 2-level system, you can actually have twice the data, because each one can be worth 2 bits instead of just 1. Each level can represent 2 bits instead of just 1. Then you can actually send double the data without increasing your baud rate. And that's something else we didn't talk about with digital signals, is your baud rate. So how often this signal changes. So is this once every second, once every minute, once every hour, once every microsecond, once every millisecond, once every femtosecond, once every yoctosecond, right? That's what's going to determine your baud rate. Or in other words, how many of these signal changes are you allowing per minute? So the way this normally works is that you, again, in digital have 2 separate camps. So within digital, within the specific, we'll just go with 2-level, not multipole, what's it's called, multipole or multi-level signals. It's much easier to understand with one signal. Within the digital camp, you have what's called a async, or asynchronous and synchronous, right? And the way synchronous works is you have a clock frequency that's just, chugging along there. And then what happens is, say, on the rising edge, you can do rising or falling, but rising's pretty common. On the rising edge of everything, you have your data. So this would be like this, and then, so this would be 1, and then on the rising edge again, you measure 1, and then on the rising edge here, you measure a 0, and on the rising edge here, you measure 0, and this would be 1, 1, 0, 0. Right? That's the way a synchronous signal works. It measures on the rising edge of the clock signal. So it takes this, whenever there is a rising edge, it measures this signal, right? Asynchronous does is it has a set time. So in fact, you just have your data here, and it looks and it says, every set time period. So it's going to look here, right? and then it's going to say that's a 1, and then it's going to look here, and it's going to say that's a 1, and then it's going to look here, and it's going to say that's a 0, and then it's going to look here, and then it's going to look here, right? Oops. Right? And it's going to look every specific time period, which is specified by the spec. So, you take, for example, the serial port, like on this Arduino I've been showing you. That's specified at like 9600 baud. So that means 9600 times a second it's going to look, right, essentially, for a bit. But the baud rate is specified, so it knows exactly how many rising edges or falling edges, how many times to check the data, if you will, every second. So it knows exactly when, and so does the thing that's sending it. So it can start checking, and then what usually happens is it has a some sort of input signal to tell it when to start. So it's like, this tells it to start looking, so this is ignored. This is just sort of like start. Then you have the actual data. Then you have a stop signal, right, which could be like, and this just sort of means the data's in between these two, look in between them. You can also have that with synchronous as well. That's pretty common. But so those are different methods of sending data via digital or analog systems. There's multiple ways to do that, and you'll find that digital is used very frequently as well as analog, because analog you have a lot of like TV signals and audio signals are sent this way. Digital, just a lot of data lines are sent this way. And very few things are sent this way because it's very difficult to measure the signal at different levels. However, if you're badly in need of higher baud rate, this can be very helpful. And so things that are synchronous versus asynchronous, right? You have like UART is synchronous, whereas SPI is asynchronous. UART is asynchronous, and SPI is synchronous because SPI is a clock signal. Okay, so like I2C has a clock as well. That means it's going to check on the rising edge of the clock. It's the data rate isn't specified. It's specified by the clock rate in that specific instance. So those are sort of the basics of electronic communication. I hope you enjoyed watching and you learned something.